All right, let's continue with a few more examples. Continuing on. This thing, we're asking the question, what has derivative 2 raised to 2 times x? Okay, so we got to think this through, and we say, okay, let's leave that 2 there. I don't know, does the 2 matter? Let's just let them sit there and think this through. If this was just x, we could apply the power rule, and we would say 1 over n plus 1. Here our n is equal to 1. And so we have times 1 over n plus 1. That would be 1 plus 1 times x raised to the n plus 1, 1 plus 1. I'll come back to the plus c, but for now we're just kind of working this through. Let's just see if this works. 2 times 1 over 2 x to the second power. Wait a minute here. If we let this be, then all of a sudden we've just got x squared. Did that work? Let's see. I don't know. Is x squared plus c the answer? Well, yeah. If you take the derivative of x squared plus c, you do in fact get 2x. So it would appear that having a constant being multiplied out in front of a variable guy, you can just do the anti-differentiation for the variable guy and leave that constant kind of out front. Just like when taking the derivative, the process of the derivative, you could leave a constant multiple out front and just worry about the variable guy. Let's see if that same thing works with example B here. -2, integral of -2 raised to the times t raised to the third power. We'll just let that -2 sit out front and we'll focus on the t. In this case, our n is equal to 3. So we'll have times -2 times 1 over 3 plus 1, t raised to the 3 plus 1 power, plus our c. And what do we get? Well, we get -2 over 4 times t raised to the fourth power is equal to, and I know I'm sorry I left the c alone there, -1/2 t to the fourth power plus c. And does that work? Well, let's check it. We'll take the derivative of this thing, -1/2 t to the fourth plus c. Take the derivative of it. We will get -1/2 times 4 t to the third power, which is equal to -2. Reduce those things away. T to the third, sure enough, it checks. Again, it appears that the constant number being multiplied by variable, just worry about the variable, do the anti-differentiation, and the constant will come along for the ride. Okay, now, here we have to remember our differentiation formula for a base exponential raised to a power. And it turns out that is ln of 8 times 8 raised to the x power. Okay, so we want the result of this thing to have whatever we come up with for the answer here of this integral. We want it to have derivative of 8x. So 8x comes to mind. The problem is if I go to check 8x and take the derivative of it, so I'm kind of deliberately leaving room, you can probably see the punchline here, I'm going to get ln of 8 times 8x. But I don't want the ln of 8 because there is no ln of 8 in my integrand. So how could I make that ln of 8 go away? Well, I need an ln of 8 to show up. And that'll make it reduce when I take the derivative. So it would seem that my antiderivative here would need to have, just like the power rule needs to have something to counteract that exponent that drops down, I need to counteract that constant that shows up during the differentiation process when I'm anti-differentiating. I need to counteract that constant by multiplying by 1 over that constant when I take the integral of an exponential. So our final answer here, because don't forget your constant, is 1 over ln of 8 times 8 raised to the x power plus c. Okay, so let's actually formalize some of those ideas that we have just recklessly done so far. Formalizing some of the ideas that we've just recklessly not brushed under the rug so far. Limits are nice, and so derivatives act nice. I've said that before. But if limits are related to derivatives, and derivatives are kind of the inverse relationship of integrals, one would hope that sort of we have another nice set of rules here, and we do. So properties of indefinite and, it turns out, definite integrals, which we'll get to later. So got to use some capital notation here, and actually the F and G don't need to be there, because the way I've got it is focus on the words. You can split integrals over different expressions being added or subtracted. So in other words, if we had f of x was x squared and it was being added to 3x for g of x, we could break this up into two separate integrals and apply some power rule action and do them. Well, what about that pesky 3? We don't have any way to deal with that yet. All we have is the power rule, but we've seen a few examples where we've logicked it through where that constant out front didn't actually hurt anything. And sure enough, in no way, shape, or form is it accurate to say you can factor out a constant out in front of an integral, but it sort of looks like that, and you can remember it as that. That multiplication by a constant to a variable expression in an integrand does not impact the result. And so you can sort of push that constant k outside the integrand and multiply it by the result of whatever you would get when you would integrate that. So in my above example, if I had 3 times my x, f of x being my x expression, I could write this integral as 3 times the integral of x dx, and now I have a rule for it. I could do the power rule and come up with the result that we saw earlier. Let's see this in action. What those two rules basically say is I'm not going to make you rewrite this as integral 5x to the third power dx minus integral 7x squared dx. No, we're just going to say that, okay, I know I can split up the process of integration over integrals, and I know that the constant won't affect the result, so I can just kind of focus on integrating with the power rule here, each of those individual expressions. So when I do that, I get 5 times 1 over, well, that's going to be the same as 5 over, times x to the, 3 plus 1? So the exponent would be 3 plus 1 that I have to counteract, minus 7 times x to the 2 plus 1, so I got to divide it by 2 plus 1, plus 3 times x to the 1 plus 1 power, so to counteract that exponent that's going to show up, I got to divide by 1 plus 1, plus 4. All right, power rule, really? Yeah, let's think of that as 4 times x to the 0 power, just like we did with derivatives. X to the 0 plus 1 power gives me 0 plus 1 as my denominator, plus c. 5/4 x to the 4th power minus 7/3 x to the 3rd power plus 3/2 x to the 2nd power plus 4 over 1 is 4, x plus c. And I encourage you, pause this right now and calculate that. Take the derivative of that expression, and you will see that it is, in fact, our integrand. One thing I haven't really mentioned is that when you have an expression like f of x, we always follow it with dx or dt. And we've seen these are differentials, and we'll kind of get into them a little bit. But for now, these tell you what the variable you're integrating with respect to. And it turns out in future maths, you'll see expressions like x, y, dx. We've done a little bit of this with implicit differentiation, where we had to keep track of multiple variables. But this actually doesn't show up in Calc 2. It shows up in Calc 3, where you'll learn to take the integral of multiple different variables in the same integrand. So for now, just thinking that dx is the differential that tells you what variable you're integrating with respect to. And we'll get into it more when we talk about Riemann sums down the road. Don't need to know what that means yet. Okay, the rest of these are just kind of different problems. Let's see what we could do here. And these are examples to show you that a little bit of algebra can really help. So looking at the integral of x squared plus 4 times the third root of x, all divided by x, you know what? We should look at that and say, hey, I have a common denominator. I can split this thing up as x squared over x plus 4 over x times, and x to the third root of x is x to the 1/3 power. Well, and that was just a bunch of algebra skills, but by doing that, I turned something hideous, a quotient, which it didn't look like, because I certainly don't have any quotient rules for integrals yet. All we have is the power rule. But by doing a little bit of algebra, we turned it into the integral of x plus the integral of 4 over, let's do the quotient rule, 4 times x raised to the negative 2/3 power. And now we sure can use the power rule to evaluate this thing. To do it, we're going to have, remember that the exponent on 1 is x, so x to the 1 plus 1 times 1 over 1 plus 1, plus 4 times x negative 2/3 plus 1. Negative 2/3 plus 1. That is what? That is 1/3. So we're going to have 1/3 plus 1. No, negative 2/3 plus 1. Same expression, but that simplifies to 1/3. I'm sorry, I shouldn't try and do things in my head. So 1/3. And then plus c. Tidy that up, get 1 over 2x squared plus, that's the same thing as 12, x to the 1/3 power, and you can leave it as 1/3 power, or you could put it back into the third root if you prefer. Either one is good, neither one is better in this case. This one, I can't do that to the next one, part C. You can't break that up into multiple fractions, and I sure don't see how I can use any kind of exponent rules to simplify that because I've got some addition in the denominator. However, that's the same thing as integral of 4 times 1 over 1 plus x squared dx. And we saw that we can just, pop that 4 outside of the integral because it's a constant being multiplied, 1 plus x squared dx. And so now the only tool I have is to think of this as the derivative of what? And this is not an obscure one, but not one we use every day, but an incredibly important one that you'll see a bunch in future classes, so I kind of pull it out periodically. 1 over 1 plus x squared is the derivative of arctangent, inverse tangent. So that integral is 4 times arctangent plus c. What about tangent times cosine? What is this the derivative of? I don't know. Let's see if we can do a little bit of algebra or trigonometry, if you will, however you want to call it. I don't like mixing sines and cosine, or tangents and other things. I like everything in terms of sine and cosine. Sine of x over cosine of x is what tangent really is, times cosine of x. Oh, snap. This integral is really just sine in disguise. So pause and figure that one out. What has derivative of sine? Well, cosine has derivative negative sine. So negative cosine will have derivative sine plus c. And that's it for examples of integration. Next, we're going to talk about initial value problems.